the linear approximation, so let's say comparison with linear approximation. They're very closely related. The linear approximation says the change in f over the change in x, that's the left-hand side of this thing, is approximately f prime of a for b near a, and b minus a is equal to delta x. All right? This statement, which is in the box, which is sitting right up there, is the statement that this change in f is actually equal to something, not approximately equal to it. It's equal to f prime of some c. And the problem here is that we don't know exactly which c. So this is for some c between a and b. All right? So that's the difference between the two. And let me elaborate. A little bit. If you're trying to understand what f of b minus f of a divided by b minus a is, the mean value theorem is telling you for sure that it's equal to this f prime of c. So that means it's less than or equal to the largest possible value on the largest value you can get, for sure. And this is on the whole interval. And I'm going to include the ends, because when you take a max, it's sometimes achieved at the ends. And similarly, because it's f prime of c, it's definitely bigger than the min on this same interval here. This is all you can say based on the mean value theorem. All you know is this. And colloquially, what that means is that the average speed is between the maximum and the minimum. Not very surprising. All right? The mean value theorem is supposed to be very intuitively obvious. It's saying the average speed is trapped between the maximum speed and the minimum speed. For sure, that's something, and that's why, incidentally, this wasn't really proved when Newton and Leibniz were around, but let's write this so that you can read it. Average speed is between the max and the min. But nobody had any trouble. They didn't disbelieve it, because it's a very natural thing.